Okay, welcome back, everyone. As usual, please turn on your video, share your video if you can. I'm going to discuss the theory of extremal length today. Just to set the stage, let me point out what we're going to discuss is part of the general issue of moduli spaces in the complex analysis in one variable moduli of Riemann surfaces. So a typical moduli space you might already be familiar with is the moduli space of complex tori. So a complex torus can be represented as X is the complex plane modulo a lattice, Z plus tau Z, where tau is in the upper half plane. So the set of all complex tori is, in some sense, isomorphic to the upper half plane. It's itself a complex manifold. But we want to identify points in this space if there exists a conformal isomorphism. Conformal isomorphism, X to Y. Or maybe let's call this X tau, so X tau 1 to X tau 2. And it turns out that that happens if and only if there's an integral Mobius transformation that relates the two values of tau. So in fact, M1 is equal to the upper half plane modulo the action of SL2Z. There's another space, which is also familiar, M04. Actually, there's two versions of this space. Let me say the one that will be closest to what we're going to do today. This is just the set of pairs consisting of a Riemann sphere and then some points, Q1, Q2, Q3, Q4 on the Riemann sphere. And these are ordered. You can say which point is the third, and they're distinct. And again, we say any two configurations of 4 points on the sphere are equivalent if there's a map, conformal map from the sphere to itself that sends the QIs to the other QIs. Well, we know there's lots of Mobius transformations available, so you can always change coordinates so that the first 3 points are 0, 1, and infinity, and then the last one is some number lambda, which has to be distinct from these 3 points. And so this moduli space is isomorphic to the Riemann sphere, but we have to remove the points 0, 1, and infinity. And then the isomorphism is given by the cross ratio, lambda. So that's the moduli space of 4 tuples of points on the sphere. We can also look at, so to speak, the moduli space of the unit disk. So this we might say we take as our set the set of X, which are subsets of the complex plane or of the Riemann sphere, where the complement consists of 2 points. So cardinality of C minus X, it contains at least 2 points, and X is simply connected. And then by the Riemann mapping theorem, we know that every such domain is isomorphic to the unit disk. And so this moduli space is a single point. And now we might do something slightly different, which is we might take points Q1, Q2, Q3, and Q4 on the boundary of these domains in the plane. So we take Jordan curves with 4 marked points. And this is what's called a quadrilateral. So it's a Jordan domain plus the choice of points Q1, Q2, Q3, and Q4 in its boundary. And they're cyclically ordered, consistent with the orientation of Q. And now one quadrilateral is isomorphic to another, say to the unit disk. So there is a Riemann mapping to the unit disk, and it will send these points to some new points on the unit disk, on the circle. So indeed, the set of quadrilaterals is isomorphic to the set of 4 tuples of points on the boundary of the disk by the Riemann mapping theorem. And as in the case of M04, we can arrange that 3 of the points are 0, 1, and infinity, but then the 4th point is just a point on the circle. Well, we could also replace the disk by the upper half plane. And then we could arrange that the points Q1, Q2, and Q4 were the points 0, 1, and infinity. And then our final point would be at some number lambda. And lambda is an invariant of this quadrilateral. So in other words, this lambda, it's what measures the modulus of the quadrilateral. It's a number which says what the shape is of this object up to conformal isomorphism, as is this lambda here, as is this tau in the upper half plane, provided we take the quotient by SL2Z. And so the difference between M04 and the space of quadrilaterals is there's some sort of reality condition built in, because lambda ends up being a real number. And in fact, it doesn't range in 0, 1, infinity. It ranges between 1 and infinity. It has to lie on this segment. So the moduli space of quadrilaterals is isomorphic to the interval, open interval from 1 to infinity on the real line by this number lambda. And I call this special quadrilateral Q lambda. Another thing we could look at is the moduli space of doubly connected regions. So a doubly connected region is a region whose complement consists of 2 connected components. So let me again call this X, contained in the Riemann sphere. So X should have 2 components to its complement. It should be topologically an annulus. Maybe I'll call it A instead of X. And as in the case of the unit disk, it's nice to exclude the degenerate case where one of those components is a single point. That's what we excluded here. Was we wanted that the complement of X was not just a single point or the complement of the space, it was the whole Riemann sphere. So it's doubly connected, and the components of neither component of the complement of A is a point. And what we will shortly prove is that every such annulus is isomorphic to the standard annulus AR, where 1 is less than R is less than infinity. In here AR, I introduced this last time, it's the annulus where the inner radii and the outer radii are R. So it's the set of Z. 1 is less than the absolute value of Z is less than R. And then it will turn out that these annuli are all distinct from one another. And so that's the moduli space of annuli can be identified with this interval from 1 to infinity. Now, for reasons that will become clear when we talk about extremal length, it's a little more natural to think of this annulus in the metric dz over the absolute value of z. And in this metric, it becomes a Euclidean cylinder of height log r, and h, and of circumference 2 pi. And so we define the invariant of A to be equal to the modulus of, in terms of this unique R, such that A is isomorphic to A sub R. And we define it to be the height over circumference of the corresponding Euclidean cylinder looks the same as this one, that's conformally isomorphic to it, and that's the value log r over 2 pi. So then with this as our invariant, we see that the moduli space of annuli is isomorphic to the interval from 0 to infinity by the modulus. Okay, now there's a couple of questions that are raised here. But before they come to that, let me just mention, I'm going to give a talk at Stony Brook this afternoon. So if anyone is interested, I'm going to put the link in the chat. And this will be a somewhat elementary talk about triangle groups and billiards. And when it will involve a discussion, not of these moduli spaces, but of something very similar, the moduli space of Riemann surfaces of genus G, where G is bigger than 1. And it turns out that this moduli space, G greater than or equal to 2, is in many ways very similar to the moduli space of tori, but it turns out its dimension over the complex numbers is 3G minus 3. Okay, but that takes us in a direction outside of the complex plane, which is not where this course is headed. We're working on more concrete objects like these annuli in the plane. Okay, so that was a brief introduction to the theory we're going to discuss today. So let me just sum up some of the statements. So the first theorem that I sketched the proof of is that every quadrilateral Q is isomorphic to Q lambda for a unique lambda 1 less than lambda less than infinity. And Q lambda is the upper half plane with the marked points 0, 1, lambda, and infinity. And then there's an allied theory for annuli. Let's say an annulus is non-degenerate if the components of its complement, neither one of these degenerates to a point. So every non-degenerate annulus A is isomorphic to A sub r for a unique r between 1 and infinity. Now, there's something that's important to address here that's not hard, which is the uniqueness of R. So why is this R an invariant of the annulus? Maybe it's true that somehow there's a Riemann mapping between AR and AS when R is not equal to S. So could there be an isomorphism from AR to AS? Could there be a conformal map that sends one to the other when R is not equal to S? In fact, there can't be. How would you prove that?
You could use the length of the core curve.
Ooh, that's a good proof. So Catherine is proposing that we say, well, this guy has a hyperbolic metric on it. And so an invariant of it is this core geodesic. And we can compute the length of this in the hyperbolic metric and see that the length determines R or S. And so that's a conformal invariant that allows us to distinguish these. How about a more elementary proof if you didn't know about the hyperbolic metric? Can you propose a different way to show such an isomorphism doesn't exist? This situation is very tempting. It's very symmetric. I think you should really reflect on what might be possible here. Okay, I think you should really reflect on what might be possible here. Anyone have an idea?
Can you use Schwartz reflection?
Yes, thank you, Louis. How would you use Schwartz reflection?
Well, I think you could just keep on reflecting over the boundary of the circle.
Okay, so in fact, if you had an isomorphism like this, let's move the domain and range farther apart. What you could do is you could reflect through the inner boundary here. You get a circle of radius 1 over r, and reflect through the inner boundary here. And by the Schwartz reflection principle, your mapping F would extend to this larger domain and still be analytic in a homeomorphism. And then you could reflect through the outer boundary, and you'd get a circle of radius r squared. And over here, you get a circle of radius s squared, and you prolong your map to this bigger region. And then if you keep reflecting, keep developing this, at the end of the day, the only thing that will be missing in the domain of F will be 0. And so its domain will become C star. And the domain over here, the target over here will become C star. And F will be an isomorphism from C star to C star. And now what can we say? Let me ask Louis, how would you finish the proof?
You can fill in the singularity.
True. So in fact, since this function is bounded in the neighborhood of 0, since 0 gets sent into the region inside the disk of radius 1, we get a map from C to C. And in fact, by the same token, we get a map from the Riemann sphere to itself. So what can we say about F?
It's a linear fractional transformation.
Yeah, that's right. And what does its formula look like? It has some special properties that came out of the construction. For example, it sends the complex plane to itself.
It fixes 0 and infinity. So B and one of the other two of the coefficients are fixed.
Okay, but so what's the formula for F?
Should be, all right, it's like a dilation, I think, or a rotation.
Yeah, that's right. So what we can deduce is that F of Z that we started out with as a map from 1R to 1S is just a multiplication by a constant. It's an automorphism of C star, and it sends the unit circle to itself. So the absolute value of alpha is equal to 1. In other words, it's a rotation, but that implies that R is equal to S. So that shows that R really is an invariant of the annulus. It also shows you that the automorphism group of the annulus just consists of rotations, because if R were equal to S, then this proves that F is given by multiplication by alpha, except we assume that F sent S1 sent the inner circle to the inner circle. It's also possible that F interchanges the inner and outer circles. So the automorphism group of the annulus is the semi-direct product of the circle with a transformation that interchanges, like Z goes to R over Z, that interchanges the inner and outer boundaries. Okay, so that shows uniqueness. What about existence? So let me say I already sketched the proof of this guy. This is basically the Riemann mapping theorem. And the proof of this will also be by the Riemann mapping theorem, but we're going to have to soup it up to deal with this doubly connected region. And so the actual theorem here is, oh, I forgot the word. Sorry, here we go. Every non-degenerate annulus is isomorphic to this. We can actually say every annulus is isomorphic to A of R, for an echo, or it's isomorphic to the punctured disk, or it's isomorphic to the punctured plane. And these are the degenerate cases that we'll usually exclude when we talk about annuli. Okay, so let me just sketch the proof of this. This is fairly familiar. So what we do is first arrange that A separates 0 and infinity. So this is a doubly connected set. So its complement consists of two connected pieces. Pick a point in one, send it to infinity by a Mobius transformation. Take a point in the other, send it to 0. That's easily done. So we can imagine that our annulus looks something like this. Its complement contains the point at infinity. And in fact, one component of the complement contains 0, the other contains the point at infinity. And now what we do is we take the preimage of the annulus under the exponential map. So the annulus is now sitting inside of C star. The universal cover of C star is the complex plane by the exponential map. And so we just let S be the logarithm of A. And what we observe is that because of the way we've normalized A, the fundamental group of A, which is generated by a loop that goes around 0, goes isomorphically to the fundamental group of C star. So pi1 of A under this inclusion maps isomorphically to pi1 of C star. And so when we take the universal cover of C star, we also get the universal cover of A. So by log A, I just mean we take the full preimage of A under the exponential map. And what we'll get is some sort of region in the complex plane, and it's invariant under the deck transformation here. You see h of z equals z plus 2 pi I. That's the deck group for this covering map. And so this region, the logarithm of A, is invariant under H. And S minus H, mod H, is isomorphic to A. But now the most important thing is that now pi1 of S is trivial. It's simply connected. Now there's a couple of degenerate cases to think about. So if A equals C star, then S is the whole complex plane. And so let's exclude that case. So that's one of the possibilities. So now assume that A does not equal C star. This implies that S is not equal to C, but even better, when you have a point that's not in S, then its whole orbit under H is not in S. So this is simply connected, and it's a simply connected subset not equal to C. So S is isomorphic to the upper half plane. So the next step is to just choose this isomorphism, this Riemann mapping from S to the upper half plane. And what that gives us, putting it together with the exponential map, is that we have A is isomorphic to S mod H, and then this is isomorphic to the upper half plane mod G, where G is now an automorphism of H, because after all, little h That is, it has one fixed point on r hat, the boundary of the upper half plane. And then we can put this fixed point at infinity. That is, we can change coordinates so that g of z is z plus 1. And now we can define a map q from the upper half plane to the punctured disk by q of z is e to the 2 pi I z. And this map is a covering map. And what's its depth group? It's g. When you add 1 to z, this changes q of z plus 1 is e to the 2 pi I times e to the 2 pi I z. And e to the 2 pi I is 1. And in fact, that's the only ambiguity in 2 points map to the same point under the exponential map, if and only if they differ by a multiple, an additive multiple of 2 pi I. And so, this Q presents the punctured disk as the quotient of H mod G. So H mod G is isomorphic to the punctured disk when G is parabolic. So that's the other, so to speak, degenerate case of the theorem. And then the second thing that could happen is that G of Z is hyperbolic. That is, it has two fixed points on the boundary of the upper half plane. And we can move these fixed points so that they're 0 and infinity. And then G of Z is lambda Z for some lambda greater than 1. This is not the lambda that appeared in the definition of Q lambda. And now we do a trick that we've already discussed once in this class, so I won't dwell on it too much, but this is neat. So we have the upper half plane, we have the action of multiplication by lambda. So we're trying to now construct a quotient map, just as we did here. Let me call it pi. That's going to send the upper half plane. It's going to be slightly convenient to send it into the annulus between 1 and 1 over r, rather than it turns out that you can take pi to have the form z to the I alpha for some positive real number alpha. And the key point is you want pi z to be pi lambda z. Just as here, we wanted q of z plus 1 to be equal to q of z. We want it to be invariant under the deck transformation. And in fact, we want lambda to be the only automorphisms that satisfy this equation. And so what is pi of lambda z? That's lambda to the I alpha times z to the I alpha. So what we want is that lambda to the I alpha should be equal to 1. And this is e to the I alpha log lambda. Now at this point, it's interesting to observe that this geodesic Hello?
Hi, we can hear you.
Did that fix things?
They're working okay for now.
Okay.
You've just been freezing up for like a few seconds at a time and then longer.
Okay.
Just, yeah.
I see. And on my side, I've been hearing this kind of patter in the noise in the audio feed. Okay, let's proceed for a little bit. And if there's an interruption, we'll restart the Zoom session. Okay? So yeah, something very strange happened. Something said recording, something about recording starting, but my recording is already starting. So it's a little odd. Sorry for that interruption, everyone. Okay, so let's go back to where are we in the proof? We're figuring out what the value of alpha should be. So we want I alpha L equal 2 pi. So we set alpha equal 2 pi over L. And then indeed, we get a map to this annulus. If you're interested in what the annulus is, the way this mapping works is that the positive real axis is, how is that mapped? Zi alpha is just x I alpha log z. So along the positive real axis, this number is real, and we're just applying e times a real number. So it goes, this part goes to the circle. And the point 1 here is also f of pi of 1.
Kurt, could you adjust the board? The right edge is cut off.
Oh, thank you. Okay. And then if we want to know what the inner radius is, we just need to look at where -1 goes, because the negative real axis goes to the inner boundary, and that would be pi of -1, which is e to the I alpha, and then the logarithm of -1 is pi I. So that's e to the minus alpha pi is equal to 1 over r. And so at the end of the day, we get a nice relationship between the length of the geodesic and this inner radius r. Those are two different invariants of the annulus, and one determines the other, as Catherine pointed out. So we get alpha equals 2 pi over L, and log r is equal to alpha pi. And so log r divided by 2 pi, this is the modulus of our annulus. And it's equal to, so I have to divide this by pi, and I guess I hope I have this right. It's, right, so alpha is 2 pi over L. So log r is 2 pi squared over L, and then I divide this by 2 pi and I get pi over L. Okay. So the modulus, so what we've proven is that any annulus is isomorphic to the standard annulus of radius r. This, of course, is isomorphic to the annulus between 1 and r by inversion through the circle. And that its modulus is related to the length of its core geodesic in this simple reciprocal fashion. So just to explain the reciprocal, in the hyperbolic metric, when you have a very tall annulus, so height is large and c is small relative to the height, so that the modulus is much greater than 0, and you take the core curve, which is just the curve that's halfway up at height h over 2, then in the hyperbolic metric, this is sort of a flat metric picture. In the curvature -1 picture, where this is complete, what it looks like is you have these exponentially flaring ends. And then this chord geodesic is very short. And in fact, its length, as you can see here, pi over L, or its length is pi over the modulus, which is pi times the circumference over the height. So as the height goes to infinity, the length of this geodesic goes to 0. Okay, so that's the classification of annuli. So we see those two things are rather closely related. Now, one thing that's really nice about these annuli is that we have these flat models for them. They're very simple geometrically, and we'll see soon that those flat models are very special. They're really the right way from many perspectives to look at an annulus. But we didn't give a flat model for our quadrilaterals, but there is an obvious one. So a standard quadrilateral is given by the rectangle RAB, which is just, if you like, it's the region 0A cross 0B in the complex plane, thought of as sitting inside of R2. So in other words, its vertices are 0A, IB, and then this point out here is A plus IB. This is our rectangle RAB. So this is a quadrilateral if we mark the vertices, and we have to choose a way to mark them. So we mark the 0 first, and then we go in the required counterclockwise direction around the region. So this is another form of a standard quadrilateral. And so the length of this side is A, and the length of this side is B. Just as in this, we have these two dimensions, H and C, in this standard flat annulus. Now, of course, if you expand and contract lambda and A and B by the same factor, you don't change the modulus of the annulus. So this is of the quadrilateral. So this is isomorphic to our TA, TB for any t greater than 0. Moreover, you can prove that those are the only isomorphisms between rectangles that preserve their vertices. And how do you do that? Exactly the same way as we did for annuli. If you have a map from a rectangle isomorphically to another rectangle, and by this I mean you have a conformal map that sends vertices to vertices in the right order, then this edge goes to this edge, and so you can Schwartz reflect to get a map on this larger region, and then you can Schwartz reflect again, and Schwartz reflect again, and Schwartz reflect again, and at the end of the day, you conclude that, again, that F is just a map of the plane to itself, and so it must be a dilation, and therefore the only invariants are the only real invariant is this ratio B over A. So we define the modulus of RAB to be this ratio A over B. Okay, so this region is in some ways much simpler than the region I drew before, Q lambda, which is the upper half plane with 0, 1, lambda, and infinity. And in fact, every Q lambda is isomorphic to one of these rectangles. And of course, it's unique up to scaling A and B. So one way to get rid of the scaling is to require that the area of the rectangle is equal to 1. So the product between A and B is 1. So let's make that into a theorem. Every quadrilateral is isomorphic to a unique rectangle, RAB, with AB equal to 1. this is, well, we start with our quadrilateral Q, and we already saw that by the Riemann mapping theorem, it's isomorphic to Q lambda. So actually, the only thing we need to do is find a conformal isomorphism between Q lambda and a rectangle. So I claim Q lambda is isomorphic by a Riemann mapping F to some rectangle. And indeed, the way you do this is you consider omega, which is the one form, d zeta over zeta, dz times z minus 1, z minus lambda in the upper half plane, but we put a square root in here. Now, you might worry, as you should, whenever you see a square root, about whether or not this is well defined. But this denominator only vanishes at these 3 points on the real axis. So it's nowhere vanishing in the upper half plane, which is simply connected. So there exists a single value branch of the square root, provided I only let z range in the upper half plane. If I tried to extend this to the whole plane, it would become multi-valued. But on the upper half plane, there's a well-defined single value branch of the square root. And then we let f of z be just any indefinite integral of this one form omega on h. And what we find is that, so then df dz, or then df is equal to omega. In other words, f prime is equal to this expression with the dz just replaced by a 1. And we can normalize this expression so that when this is, let's look at what this product looks like here. So we have a 0 at 0, a 0 at 1, and a 0 at lambda. So this function, z minus 1, z minus lambda, looks like this. It's grosso modo like z cubed. So it comes up like this, then it goes down like this, and then it goes up again. So you can see that on this region, from my infinity to 0, it's negative, then it's positive, then it's negative, and then it's positive. So when we take the square root, we can arrange that it continues to be positive here, but here we're taking the square root of a negative number, so it's imaginary, purely imaginary. Here it's purely imaginary, and in fact, and here it's positive. In fact, we can only arrange for sure that it's real here if we want to make it continuous. So let's say it's real here, it's real on these intervals, and it's imaginary on these intervals. Now, and nowhere 0 on those intervals. So what does that mean when you integrate this function along the real axis? What happens is that starting at 0, you're integrating something that's real, and we can arrange that it's positive. So it starts to go like this. This is f of 0. And then you hit 1. And at 1, the derivative becomes imaginary. So you start going vertically until you hit f of lambda. And at f of lambda, it becomes real again, but this time negative, until we come over to f of infinity. And then from infinity to 0, it's imaginary, negative imaginary, and you come back to where you started. And so the boundary of the upper half plane maps going once around to the boundary of a rectangle, R. And that's at least a sketch of the proof of the fact that there is a conformal map from the upper half plane to some rectangle that sends the 4 vertices of this quadrilateral to the 4 vertices of the rectangle. Okay, and then this rectangle, maybe f of 0 is not 0, but I could normalize so that it's equal to 0, because when I integrate, there's a constant of integration that appears here. And then this R literally is R of AB for some A and B. And so that completes the proof. Okay. So with this in mind, we now make a definition, which is that the modulus of a quadrilateral Q is equal to the modulus of RAB is equal to A over B for the unique RAB isomorphic to Q with AB equal to 1. Great. So we've classified annuli and we've classified rectangles. We've solved the moduli problem for these two types of frequently occurring subsets of the complex plane. And it's interesting that they vary, and it's interesting that they have a parameter that can be changed, and that parameter uniquely determines the conformal structure of the region. By the way, you might wonder, looking at this theorem, can you tell me what the modulus is of Q of lambda? What is the modulus of Q of lambda? And actually, the proof I gave tells you exactly how to compute it. You see, what is A? A is equal to the integral from 0 to 1 of omega. This one form that we've written down here. And that's no big deal. The integral from 0 to 1 of dx over x times x minus 1 times x minus lambda. That's a good old real integral. I'll put in absolute values with a square root in it. I'll put in absolute values just so it's clear the determination of the square root doesn't make any difference. And B is similarly the integral from 1 to lambda of exactly the same expression. And so if we take the ratio of those two functions, we get an explicit determination of the value of the modulus for the quadrilateral Q lambda. And as you can see, there's some hidden relationship to elliptic integrals. I won't go into that, but it's obviously hidden here because these are elliptic integrals. An exact expression can be given here in terms of elliptic modular functions. But we won't pursue that. What we want to pursue is the geometric idea that quadrilaterals, every quadrilateral is secretly a rectangle, every annulus is secretly a right annulus of some height and circumference. Okay, so it was a beautiful breakthrough by Arnie Bierling to give a very simple way of saying what the modulus of a quadrilateral and what a modulus of an annulus are. And this characterization of the important invariant of this region, namely its modulus, is very amenable to estimates. The way I defined it, you have to go through the Riemann mapping theorem in both cases. So it's hard to say, given a region, as I mentioned last time, we could take a square of side length 4 and inside of it put a square of side length 1, then we have an annulus. What is the modulus of A? And so we want to find an isomorphism to a Euclidean annulus of height c and height h and circumference c. What's the ratio of h over c? It looks very hard from this perspective because the Riemann mapping would be quite hard to write down. But often in complex analysis, we're happy with estimates. And the beautiful thing about Bierling's technique of extremal length is it gives estimates that go both ways. It gives upper and lower bounds on the modulus. So let me introduce this beautiful idea. Okay, so this is a conformal invariant of a path family, and it can be defined in many different settings besides the one I'm going to talk about. So here's the general setup. So omega will be a region. In fact, it could also be a Riemann surface. And we'll discuss some Riemann surface cases elementary ones as we go. And then gamma is going to be a collection of paths. Omega. Now, what is a path? Technically, it's a map from some interval AB into omega. And it should be, let's say it's rectifiable. That means that it has a well-defined length, or that the map is Lipschitz, which is enough to imply that its derivative to exist almost everywhere. And the third player is we're going to need to study metrics on our region. So this will be given by rho is rho of z dz, as usual. And what properties do we want rho to have? Well, we want rho to be positive, or at least non-negative. And then you might say, do you want it to be continuous? Do you want it to be smooth? Well, in fact, we want to allow rho to be discontinuous, but we do want to be able to integrate it. But we don't know what measure we want to use to integrate it again. So we're going to require that rho is a Borel function. So if you like, usually one can get away with piecewise continuous functions. The Borel functions are just a mild generalization of those, but the main thing is a Borel function is integrable, you can integrate it along a curve or over a region. It's well defined at every point. Okay, and now what we're going to do is we're going to define the length of this path family for a given metric rho. So first, what's the length of one of these rectifiable curves with respect to rho? Well, you just take the integral from a to b of the value of rho at gamma of t times gamma prime of t times dt. But we usually just abbreviate that by saying you integrate rho along gamma. And if gamma were an embedded path and rho were a smooth metric, this would just be the ordinary Riemannian length of gamma. So the idea is, in this theory, is that in our region omega, we have many paths gamma. And they're all kind of competing to be geodesics. By geodesics, I mean, what we're really interested in is the shortest path in this path family, and we don't know which one is shortest. In fact, the shortest one will depend on the metric. So we define the length of the path family in a given metric to just be the shortest, the length of the shortest curve in the path family. So we let L of capital gamma, rho, just be the inf over elements of the path family of the length of gamma. It's the shortest. Or intuitively, it's the length of the geodesic length. The geodesic, if the geodesic is the shortest curve. Now, I'm not saying it's achieved. I'm just saying by definition, it's the smallest it can be made. And now there's another invariant we can attach to this situation, which is the area of our region with respect to this metric. And that's just the integral over the region of rho squared. Now, this technique is sometimes called the length area method. And the idea is to let these two quantities compete with each other. So you'll notice that if you multiply the metric by 2, then the lengths go up by 2, but the area goes up by 4 because it's squared. So what we now do is we define the extremal length of this family with respect to rho as the ratio of the length of the family with respect to rho squared divided by the area. And then finally, we want to get rid of the metric rho. And And so here's the definition of extremal length. The extremal length of gamma omega is the supremum over all possible choices of metric rho of this quantity, the length of gamma with respect to rho squared divided by the area of omega with respect to rho. Okay, so there's a lot of soups and imps, but at the end of the day, what I want to emphasize is this. We have defined a real number. In fact, it's something greater than or equal to 0. And it's an invariant of topological data, which will be this choice of path family, plus the geometric data of this region in the plane. And it's a conformal invariant. It's a conformal invariant because the only way rho was restricted was that it had to be a conformal metric. So if you have an isomorphism between a region omega and a region omega prime, it's given by a conformal map. And if it sends the family of paths here to the family of paths gamma prime here, then the extremal length of omega gamma is just the same as the extremal length of omega prime and gamma prime, because you can take conformal metrics on omega and transport them to conformal metrics on omega prime and vice versa. Okay, so that's the abstract definition. And I think what Bierling's insight was that this general definition can now be applied in many, many concrete cases to give something interesting. And so what we need next are some path families. So let's do a prime example and see if we can do a computation. So we're going to take omega to be our rectangle RAB, and we're going to let gamma A be the set of paths that join what I'm going to call the B sides of RAB. So this side has length A, this side has length B, and gamma A will consist of these curves. That's a typical element of gamma A. So it has to cross the rectangle starting at this vertical side and ending at this vertical side. I'm not requiring that it be embedded, or even it could hit the top and bottom edges as it goes, but it has to start on one edge and make it all the way over to the other edge. Okay, so now let's try a computation of extremal length. Let's figure out what the extremal length of this path family is in the metric that we know and love, the Euclidean metric on the complex plane. So what's the shortest length of a curve that joins the B sides? Well, it's obviously the length of a straight horizontal line, and its length is A. So in the Euclidean metric, on the numerator, we get L of gamma A rho is equal to A. That's why I called it gamma A. And then we square that, we get A squared. And then on the bottom, we have the area of our region, omega, with respect to the Euclidean metric, that's A times B. And so the ratio is A over B. Pretty good. Now, does that show that the modulus of this RAB is equal to A over B? Not quite, because the extremal length is not what you get for one metric, it's the soup over all metrics. So it shows that this metric gives A over B, so the soup is at least A over B. So this implies that lambda of gamma A in the region RAB is greater than or equal to A over B. And then the main result is that equality holds. so this is the real theorem, is that for omega equals RAB and gamma, the family gamma A, the extremal length of omega gamma, sorry, I think I keep reversing gamma omega and omega gamma. I'm not sure what the correct convention is, so I'll use both. The extremal length of gamma, often people just write gamma itself, the region omega being implicit. The extremal length of gamma A is equal to A over B, which is equal to the modulus of RAB. Okay, so what's the proof? What we have to do is analyze what happens for an arbitrary conformal metric row. So consider now any conformal metric row on our rectangle. And now I'm going to use first a basic trick, which is that the integral of rho over my rectangle R is equal to the integral of 1 times rho over the rectangle. So we've seen this trick before. This is less than or equal to, by the Cauchy-Schwarz inequality, the integral of 1 to the 1/2 times the integral of rho squared to the 1/2. And this is a consistent feature of all applications of extremal length. The argument always turns on the Cauchy-Schwarz inequality, and this is how it's used. This integral is something we're going to be able to interpret in terms of lengths because it's the integral of just rho, and rho is something that likes to be integrated over curves. Here we get the integral of rho squared. That's something that likes to be integrated over a region. And so this quantity here is what? The first term is just the area of the rectangle. So that's AB, the 1/2. And the second term is the area of the rectangle with respect to rho. So it's A rho to the 1/2. Okay, now comes the interesting part. How can we relate this integral to lengths? So the idea is that what we're really doing in our AB rectangle is we're taking the integral of rho, and now let me think of it as a function of x and y. And we're going to integrate it dx dy over our region RAB. So that means we integrate first from x goes from 0 to a, and then we integrate from y goes from 0 to b. Okay, now what can we say about this first integral? So in the first integral, we fix y. Sorry, let me put it in brackets here. We fix the value of y, and we just let x go from 0 to a. So this inner integral is this. We fix y, and we look at this straight segment, gamma y, and we integrate the metric rho over that segment. That's just the length of gamma y in the metric rho. Now in the definition of extremal length, we're interested in the shortest element in the path family, and gamma y is in our family gamma A. So this is greater than or equal to the length of the shortest curve that connects these two sides. So this is greater than or equal to L of gamma A with respect to rho. So this integral here is greater than or equal to the integral from 0 to y of L, now we have length coming in, gamma L gamma, capital gamma, rho dy. Well, this is a constant. So when we integrate dy, we just get a b coming out in front. So this gives b times L gamma rho. And now we're done, because you see if we square both sides, what this says is that b squared L is less than or equal to AB times A, where A and L are the length and area, sorry, this should have been L squared, are the length and area coming from the row metric. So that gives L squared over A is less than or equal to AB over B squared, which is equal to A over B. So what we saw was that for the Euclidean metric, the extremal length of gamma came out to be exactly A over B, and this shows that for any other metric, it comes out less. And therefore, the extremal length is exactly given by A over B. That's the proof of this theorem. Okay, now what is it that we've really proven? We've proven that the modulus of a quadrilateral can be defined in terms of extremal length. So let me explain how that works. Let's reconsider a random quadrilateral again, Q. So it has these special points Q1, Q2, Q3, and Q4. So when we have a general quadrilateral, we call these two edges are called the A sides. They're well defined because the points Q come with labels. And these other edges are called the B sides. All we need is this little bit of combinatorial information to determine how to label the two sides. And once we have the A sides and the B sides, we can define this path, this family of paths gamma A. They're the paths that are, so to speak, topologically parallel to the A sides. They separate the A sides from each other and they join the opposite B sides. Now, the theorem here, this easy corollary, is that the extremal length in Q of this path family gamma A is equal to the modulus of Q. What's the proof? Well, how do you compute the modulus of Q? You find a rectangle to which it's isomorphic, and then you take the ratio A over B. But when you change Q by a conformal isomorphism to this rectangle RA over B, RAB, it doesn't change the extremal length of this path family. The extremal length is a conformal invariant. So the proof is just that if Q is isomorphic to RAB, which it is for sub A and B, then the extremal length of lambda Q gamma A is the same as the extremal length in RAB of gamma A. It's gamma A, which we just computed to be A over B, and that by definition is the modulus of Q. Okay, now here's where extremal length really shines. There's another path family here. It's the family of paths that are parallel to the B sides, or in other words, the family of paths that connect the B sides together. That's called gamma B. So when you're presented with a quadrilateral, you have two possible path families you can work with. And what do you think the extremal length is in this quadrilateral of gamma B? Well, all we've done is interchange the roles of A and B. So it's equal to B over A. In other words, it's equal to 1 over the modulus of the quadrilateral. So both the modulus of the quadrilateral and its reciprocal can be expressed as extremal lengths. Now, why is this so powerful? You see, the modulus, suppose we are given a metric rho on Q. Now remember, lambda of gamma is some sort of soup over rho of something rather. So extremal length is always bounded below by what you get for a particular metric row. So in particular, what we have is that the modulus of Q is equal to lambda of gamma A, and that's greater than or equal to the extremal length of gamma A in our given metric. But on the other hand, this particular metric gives a lower bound for the reciprocal here. So this is also less than or equal to 1 over the extremal length of gamma B in the metric row. And so the upshot is that one metric on your region gives you upper and lower bounds for the modulus immediately. Just compute the extremal length of these two path families, these two crossing path families. And each one will provide either an upper or lower bound. So let me finish by showing you an application of this beautiful fact. So this is a theorem due to Vasikovich. And it's a theorem that makes no reference to conformal geometry. It's an elementary theorem about the plane. It's really beautiful. So it says the following. Suppose we have, just to emphasize that it's not a priori a conformal statement, let's just let me call it, I'll call it Q. Let Q contained in the complex plane, or in R, let me say in R2, just for fun, be a topological disk, and boundary of Q is equal to a union of cyclically ordered arcs. Alpha, beta, alpha prime, beta prime. Then the area of Q is greater than or equal to the distance from alpha to alpha prime times the distance from beta to beta prime. So think about what this says. It's really pretty neat. So you have a pretty wild region like this, let's say. This is our region Q. And I want to figure out what the area is of Q. So what I do is I look at how close the red sides get to each other. And I call that number A, the minimum distance between the red sides. And then I look at the minimum distance, not necessarily through Q. This line could have gone outside of Q. I look at the minimum distance between the yellow sides. And then the claim is that the area of Q is always bigger than or equal to A times B. And this is really wild because it's not true, it need not be true that Q contains an A by B rectangle anywhere inside of it. And nevertheless, we get a lower bound on its area, just in terms of the product of the distances between opposite sides. Okay, so that's a beautiful elementary statement about domains in the plane. And personally, the only proof I know goes through the modulus. So here's the proof. We let rho be the Euclidean metric. Then the extremal length of the A curves in, sorry, I should have called these, I should have called these A and B. This is A, this is B. The extremal length of the A curves in the Euclidean metric is equal to what? It's equal to exactly the minimum distance between beta and beta prime. This is an A curve. So it's equal to the distance from beta to beta prime, but divided by the area of our region as squared, divided by our area squared, divided by the area of our region. And similarly, lambda gamma b in the metric row is less than or equal to the distance from alpha to alpha prime squared, divided by the area. Now let's look at this equation that's written down here. It says lambda gamma AB is always less than or equal to the reciprocal of gamma BA. We can write that as saying lambda gamma A row times lambda of gamma B row is always less than or equal to 1. And if we apply that in this case, what we'll get, we just take the product of those things, we'll get the distance from alpha to alpha prime squared times the distance from beta to beta prime squared divided by the area squared is less than or equal to 1. And so the product of these two distances squared is bounded by the area squared, and taking square roots, we get that the area is at least as big as the product of the two distances. Okay, so that shows how, without actually knowing the modulus of a region, we can still get information about it using the upper and lower bounds provided by two different path families. Okay, so as I mentioned, we will have a wellness day next Tuesday, so no class meeting. I will, however, put together some homework, but it won't be due till the Tuesday after that. I'll circulate that as soon as it's ready. And then next week, I'll finish up with extremal length, and we'll start on random processes, random walks on lattices. Okay.